Hi, everybody. I hope we are all ready to do some more chemistry today. And so let's go ahead and just dive right in and start off with our warm-up problems. So here's our first one. What I want you to do is go ahead and pause the video now, and using a periodic table and the concepts of atomic structure that we talked about last time, go ahead and fill in all of the missing information on this table. And so pause the video now and see what you can come up with. And hopefully what you came up with was the following. And so the key terms that we have to remember in order to fill out a table like this are atomic number, which is found in the periodic table and tells us the number of protons that are in a nucleus of an atom. We also have to remember that the number of electrons is equal to the number of protons in a neutral atom. And finally, the mass number, which is equal to the number of protons plus neutrons in an atomic nucleus. And that this number here, written as a superscript to the left, is our mass number. Next, go and use this information here with all of the different isotopes of magnesium to calculate what the blended atomic weight of magnesium is. So go ahead and pause the video now. See what you can come up with. Hopefully what you got was 24.305 AMU, which sure enough, if we check the periodic table, sorry, it's on the other side of me here. If we look on the periodic table for magnesium, 24.305. And so again, if you didn't come up with this, then go back and look over some of the concepts that we talked about, look at some of the examples, and hopefully see where you went wrong. And so now we're going to start diving into some new material. Today we're going to look at molecules, compounds, and formulas and some definitions there. And then we're going to spend most of today looking at how we determine molecular formulas of compounds. For instance, why is water H2O? Why is sodium chloride NaCl? And so forth. And then we're going to look at going the opposite direction. We're going to look at coming up with the names of various compounds. And as we'll see, there are very strict rules for how we come up with both of those things. And so just a couple definitions so that we're on the same page with some of the terms that we're going to use. As we mentioned earlier, a compound is a combination of two or more elements. It's important to note that a compound, when we use the word compound, we're talking about a classification. And so water is a compound because it's made up of both hydrogen and oxygen. Sodium chloride is a compound because it's made up of sodium and chlorine. Gold is not a compound because it's made up of just one type of element. It's made up of just gold. And so a compound is a word that we use to classify a particular type of matter. Is it matter that's made up of two or more elements or not? When we have various types of compounds, we have ionic compounds, which are made up of a metal. Look back here. So remember, the metals are sort of this entire left-hand portion of the table here. And then non-metals up in this right-hand portion of the table with our metalloids here in between. Ionic compounds are made up of a metal and a non-metal, or some sort of mixture with polyatomic ions in there. And we'll talk about what those are in a few minutes. We also have what we call molecular or sometimes covalent compounds, which are made up of a metal and a non-metal. And so nitrogen and oxygen, for instance, coming together would be a molecular or a covalent compound, versus copper and oxygen coming together. Now that's an ionic compound because it's a metal and a non-metal. Another important classification that I don't think I was clear on last time, which is fairly important, hydrogen is over here in the table, way up is the very first element in the upper left. Even though hydrogen is placed where it is, hydrogen is a non-metal and it's categorized as such. We'll talk about why it is where it is when we get deeper into talking about electrons and how electron arrangements lead to the table being set up the way that it is. For now, just know that hydrogen is a weird exception. It's over here, but hydrogen is a non-metal. And so again, ionic compounds, metal and non-metal, or a polyatomic ion in there, molecular or covalent compounds, two or more non-metals. When we use the word molecule, what we're talking about there is something that is the smallest unit of a compound that still retains the characteristics of that compound. In other words, a molecule is an actual thing. When we say we're talking about a water molecule or a group of water molecules, we're talking about the actual physical molecule itself. We're talking about an oxygen with two hydrogens, and it's the actual water molecule, a tangible thing. And so I like to make that differentiation so you know what we're talking about when we use those two different terms, either a compound or a molecule. Molecular formulas, which will make up a big part of our conversation today. A molecular formula shows us the number and type of each atom within a molecule. So for instance, the molecule ethanol would have the molecular formula C2H6O. This tells us that every ethanol molecule will have 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. We also have different ways in which we show these elements, in which we depict the molecules. We have a condensed formula, which in the case of ethanol would be CH3CH2OH. The difference between the two of these is that the molecular formula simply tells you the type and number of atoms, and that's it. It doesn't give you any information as to how those atoms may be connected or arranged within the individual molecules. A condensed formula starts to show us that a little bit. The condensed formula, the way this is written, tells us that 3 of these hydrogens are connected to a carbon. 2 of these other hydrogens are connected to another carbon. An O and H are actually connected to each other. And then the structural formula gives us even more detail into that. We can see here, in fact, that the sort of in the backbone of the structure, so to speak, we have a carbon and an oxygen, and then hydrogens hanging around all along the outsides. Finally, we also have molecular models, which give us more of a 3D perspective of what the actual molecule looks like within 3 dimensions. We're not going to be working much with structural or molecular models until much later in the course. These will take up a big part of what we do actually in Unit 3. But we will certainly be working with molecular formulas quite a bit and looking at what the formulas of individual molecules are. And so we're going to start today by looking at ionic compounds. Ionic compounds, as I mentioned earlier, typically metals and nonmetals, also polyatomic ions in there, and they are a major class of compounds. They consist of ions. Now remember before in the last lecture, when we talked about atoms, we were talking about things that are electrically neutral. And so the number of protons was equal to the number of electrons within the atom, so the pluses balanced out the minuses. For ions, and we're going to see in just a minute how this happens, for ions, that isn't the case. For an ion, our number of protons does not equal the number of electrons, and so the atom is now going to have an electrical charge associated with it, either a positive or a negative charge. And then just due to the laws of electrostatic attraction, positive charge, negative charge, they're going to stick together. A lot of the very familiar compounds that we know and that we use and we talk about are ionic compounds. And so table salt, common table salt that you throw on your French fries and your popcorn. Sodium chloride, NaCl, that's an ionic compound. This would be what a big block of pure NaCl looks like. And this is what it would look like at the molecular level. We would have alternating sodium and chlorine atoms. Big old sodium atom here, a big old sodium ion with a chlorine ion here. And then we can see that they're alternating in this sort of this lattice arrangement. Ionic compounds, generically from a chemical perspective, are referred to as salts. So that's another area where we just have to recognize that there is a difference in how we talk as chemists and the way that certain terms are used in everyday language. When we hear the term salt, we think sodium chloride. We think that's that spice that you are going to throw onto your food to make it more flavorful. From a chemical perspective, that type of salt, sodium chloride, is just one type of salt. It's just one ionic compound. Ionic compounds in general are always referred to as salts from a chemical definition standpoint. And so ions, as I mentioned, they're atoms or groups of atoms that actually now will have a positive or a negative charge. These charges form by electrons either being removed or added to an atom. Now, this is a very key distinction to make. The number of protons will not change. That's why I tried to emphasize so much in the last lecture that the number of protons is absolutely what defines an element. So if we're talking about a sodium ion, sodium right here on the periodic table, atomic number 11, a sodium ion is still going to have 11 protons in there. That's what makes it sodium. But now it's no longer going to have 11 electrons. We're going to mess with that number of electrons in order to form ions. If an electron is removed from an atom, remember electrons are negatively charged. So if we remove one electron, then that's going to leave us with a positively charged atom, which we call a cation. Adding electrons, now we're going to have additional negative charges in there because we're adding in electrons, will lead us to a negatively charged ion, which is known as an anion. If we look at a picture of what that might look like, then in the case maybe of magnesium, for instance. So magnesium is going to lose 2 electrons in order to form a magnesium 2+ ion. Fluorine is going to gain 1 electron in order to form a fluorine 1- anion. If we just sort of take a different look at that, oops, didn't mean to open my scanner. And so, for instance, let's look at our sodium example. And so here's a sodium nucleus in there. So a sodium ion with its 11 protons. And then if we look at how the electrons are arranged, we're not going to really worry too much about this electron arrangement. We will get into much more detail of how these electrons are set up in a later unit. But sodium has one little electron here on the very outside. And so we have 11 electrons there. Now, what's actually going to happen is one of these electrons here on the outside is going to be completely removed from the sodium atom. So once that electron is removed, all the others are still there. We haven't touched the other 10 electrons. Those are still there. And we haven't touched our number of protons. And so now we have one more positive charge than we have negative charges, leading overall to a 1+ charge as opposed to the neutral charge that we had in the sodium ion. And so we would depict that as Na 1+, showing that we're now talking about sodium with a charge of 1+. And the magnesium example that I just showed, very, very similar. In the case of magnesium, here's our magnesium nucleus with its 12 protons, electrons all arranged on the outside, and then 2 electrons out here on the very outside. Those 2 electrons are going to be removed. So we started out with 12 electrons here for a neutral magnesium atom. We've now removed those 2 electrons. And so now magnesium Still has its 12 protons. We have not affected our number of positive charges. But now we only have 10 electrons, leaving us with 2 additional positive charges compared to the negative charges. So we have a magnesium 2+ ion. Fluorine. So fluorine, over here on the periodic table, with its 9 protons, so there's our 9 electrons now on the outside as well, forgive these very crude drawings. For a neutral fluorine atom, now what we're actually going to do is add 1 electron in. We're going to add 1 electron into fluorine, so that now fluorine is going to have a total of 10 electrons. Still 9 protons, still 9 positive charges in there, but 10 electrons. So we have 1 additional minus charge as compared to our positive charges, leading us to a fluorine 1- ion. And so that's I went through all of that and showed you all of this just to make it very, very clear to you that that's what's going on when we form ions. We're adjusting our number of electrons. We're not touching our number of protons. The number of protons does not change, but we're either removing or adding in electrons to now disrupt that balance that we had before between the number of protons and electrons. Now that balance has been disrupted, we no longer have neutral atoms. We will have either positively charged ions or negatively charged ions, known as cations and anions. And so hopefully you're starting to ask yourself, okay, well, that's great, but how do I know? How can I predict what's going to happen? Metals, this is one of the reasons why it's so important to be able to differentiate between metals and nonmetals in the periodic table. Metals will lose electrons to form cations. Nonmetals will gain electrons to form anions. Not only that, they do so in a very predictable way. And so we can see here as we predict some of these charges, look at our alkali metals right here, along with hydrogen. All have charges of 1+. Our alkaline earth metals all have charges of 2+. We're going to skip our transition metals for a minute. They're a little bit different. But we can see here, and we start to see a few differences in this section too. But aluminum with its 3+, tin and lead with a 2+. But then we look at our non-metals. Don't really worry about this H-. This is a little bit funky. But our halogens, our fluorine, chlorine, bromine, and iodine, these halogens here all 1-. This row here, right next to the halogens, starting with oxygen, all 2-. Nitrogen and phosphorus, 3-. And so metals, like I said, metals are going to lose electrons to form these positive ions. Nonmetals gain them to form anions. And this happens in a very predictable way according to the column that an element is in the periodic table. And this is how we can remember it. Everything in this column here, everything in our very left-hand column in the periodic table is going to tend to form a +1 charge, plus a +1 cation. Everything in our second column is going to tend to form a +2 ion. We'll skip the transition metals. We'll come back and talk about those. They don't behave quite as predictably. But everything in our third column here, after skipping those transitions, boron, aluminum, and so forth, will tend to form a +3. Now we get to this column here, carbon, silicon, germanium, not as predictable. And so carbon and silicon, for instance, don't tend to form ions. They tend instead to share electrons. And we'll talk about those when we start talking about molecular and covalent compounds. But then if we come back over, if we start from the very right-hand side of the table, our noble gases here don't tend to form ions at all either. They tend to be completely stable and they're very unreactive for reasons that we'll talk about later in the course. We're not going to really worry about the why behind some of this for now. We're just going to know that these things happen. We come to our halogens, fluorine, chlorine, bromine, iodine, and even little astatine, or I should say big astatine, will all form -1s. Everything in this column will form a -1. Everything in this column that we're going to work with will form a -2. Everything in this column that we'll work with will form a -3. Now I say that we'll work with because when we start to get into some of this region here, some of the rules get a little bit murkier and a little bit fuzzy down in this range. Again, for reasons that we will talk about later. But for now, I mean, we're going to primarily work with things like oxygen and sulfur, maybe a little selenium, and these are going to tend to form -2s when they form ions. These are going to tend to form -3s when they form ions. Now, the transition metals, like I said, they're not nearly as predictable. So something like iron, for instance, can easily form a +2 or a +3. Manganese can form a +2 or a +4. And things can be all over the place. In fact, chromium shows a +2 and a +3 here, but chromium could even form a +7. Vanadium can form +2, +3, +5, even 6, I think. Things get very unpredictable here in the transition metals. But for everything else, +1, +2, +3, -3, -2, -1. And so you are going to have to know how to use the periodic table in order to predict the charge on ions, because we're going to use that. That's going to become very important for us. When we're naming ions, when it comes to a cation, when it comes to positively charged, all we do is it's the name of the element followed by the word ion. And so Na plus would be referred to as a sodium ion. Mg2+, magnesium ion, aluminum 3+, aluminum ion, and so forth. Anions, we do actually chop the end of the element off and add IDE instead, and then the word ion. And so chlorine with a 1- becomes a chloride ion. Oxygen with a 2-, oxide ion, so forth. Bromine with a 1-, bromide ion, and so forth. And just some examples here. With the transition metals, and we'll get into this a little bit more deeper later on as well, but since the transition metals can have different charges associated with them, we actually identify the charge in the name of the ion. And so a copper with a 1+ charge is a copper 1 ion. A copper 2 with a 2+ charge, copper 2 ion. Iron with a 2+, iron 2 ion. Iron with a 3+, iron 3 ion, and so forth. And we use Roman numerals in order to show that. And we'll show how this is used a little bit later on in this lecture. So as I mentioned before, now we're just going to add the IDE on for negatively charged ions. Hydrogen's weird. Hydrogen can form a +1 or a -1. Again, for reasons we'll talk about later, don't really worry about the why so much for now. But if hydrogen forms a negatively charged ion, it's called hydride. Fluoride, chloride, bromide, iodide, and so forth. Oxide, sulfide, selenide, nitride, phosphide, as opposed to phosphorus, and so on. Now, those are for monatomic ions, for ions that are made up of just one element. We also have a class of ion known as polyatomic ions. Polyatomic ions are groups of atoms that will tend to stay together as a compound, but now that compound is going to have an overall charge. And so a polyatomic ions are groups of ions that have a charge associated with them. There are several that you are just going to need to know that are very common polyatomic ions. And so, for instance, ammonium, it has a formula NH4 with a +1 charge. Peroxide, formula of O2 with a 2- charge. Acetate, formula is CH3COO, has a 1- charge, and so forth. These are some of the more commonly used and commonly known polyatomic ions. This is one of the only things that you do have to just flat out memorize as part of this course. You have to be able to recognize and know the polyatomic ions. You have to know the name, the formula, and the charge. Later on in the course, if I say nitrate, you're just going to have to know that nitrate is NO3 and it has a 1- charge. You're going to have to know that that chromate is CrO4 and it has a 2- charge. Cyanide is Cn and it has a 1- charge. Phosphate, PO4, and it has a 3-. We'll talk about a little bit later about what you are allowed to use on exams and so forth, and you will be allowed to use a cheat sheet. And so yes, you could have these out in front of you, but trust me when I tell you that you will make your lives so much easier if you simply know these ions. Especially when we get to talking about reactions in a couple of weeks. If you don't recognize these as being polyatomic ions when you see them, you're going to be tempted to break them apart, and that's not what happens. These tend to stay together, clump together as a group of atoms. And so that's just one of the reasons why it's going to be so important to be able to recognize them. The other reason is, we're going to talk about naming in just a few minutes. You have to recognize that when you see NO2 with a 1- charge, that the name of that is nitrite. And so chemical compounds that have that in there have to be named accordingly with that name, with nitrite in the name. And so it is key that you know these and that you memorize these. One of the best ways, I think, to memorize these are just tried and true flashcards. And I would go a step further and color code your flashcards in some way. Color code them according to charge. Maybe all of your -1s are green, all of your -3s are orange, something like that. And not even different colored cards themselves, although if you had different colored cards, that would be powerful. But even just different colored inks, or highlight something on there, make a little circle that's green. Part of the reason for that, and just sort of study habits in general, is that color coding of flashcards can just add another dimension of your studying and of your use of flashcards. For instance, with what we're doing here, you might get to a test situation or just work in general, and you say, oh, sulfate. Okay, I know that sulfate is SO4, but I don't remember the charge. You might literally, if you've used them enough, you might literally picture that flashcard in your head and say, oh yeah, sulfate was one of my red ones. All my red ones are -2s. Boom. And it's another way to help you remember some of these charges and so forth. So that's what I would do if it were me. That's how I would learn these. But however you choose to do it, I do, just like I said, I highly, highly, highly recommend that you do memorize all of these polyatomic ions. I think it will be key to your learning as we go on through this semester. And so now let's talk about how we come up with a formula, a chemical formula of an ionic compound. So we showed earlier what chemical formulas are. They show us the atoms and the ratios that atoms are in within a chemical compound. And so now we're going to look at how we actually come up with those formulas. When we write an ionic formula, and so we're talking now about, we'll start fairly simply by just looking at two different atoms coming together, a metal cation coming together with a non-metal anion. They are going to come together in such a way that the total charge on the compound is neutral, so that the positively charged cations will balance out the negatively charged anions. And like I mentioned before, we can predict the ion charge by using the periodic table. And so we can use something, for instance, called, there are actually several ways to do this. We could use something called the crossover rule, and these rules also apply to polyatomic ions, which we'll talk about and look at in just a minute. But actually, rather than going through some of these PowerPoints, let's just do a couple examples because I think this will help out. Let's say, for instance, we're talking about what happens or what our formula is going to be if sodium comes together with chlorine. We look at the periodic table and we see that sodium is going to be a 1 plus and the chlorine will form a chloride 1 minus ion. Now those are going to come together in such a way, and we're going to have enough of each of them so that the pluses balance out the minuses. Turns out that for sodium and chlorine, all I need is one of each. So I just have NaCl. Now let's say instead of sodium, I have magnesium. I use the periodic table. Magnesium's in my second column. Periodic table tells me that magnesium will have a charge of 2 plus. And chlorine will have a charge, still its charge of 1 minus. Now what I'm going to need is if I have 1 magnesium, now I need 2 chlorines to balance that out. I look at it this way. As things stand right now, I don't have enough minuses to balance out my pluses. If, however, I have 1 more minus in there, now I have a total of 2 pluses and 2 minuses. So I have a neutral compound. I have 1 magnesium in there, and now I have 2 chlorines or chlorides, which I write as a subscript. And so this 2 right here, this subscript in my chemical formula, tells me that I have 2 chloride ions. There's a 1 right here, but just like with exponents in math, we just don't write the 1, it's assumed. So I have 1 magnesium and 2 chloride ions, giving me a chemical formula of MgCl2. And so if I have maybe, let's come back to sodium with its 1 plus, but now maybe I have sulfur. Periodic table tells me that sulfur has a charge of 2 minus. And so now 1 plus with a 2 minus, I don't have enough pluses now to balance out my minuses. And so I'm going to add in another 1 plus. Now I have enough pluses to balance my minuses. And so I've got 2 NAs, I have 2 sodiums, and so I get Na2S. If we look at one that's maybe a little bit more complicated, aluminum, periodic table tells me aluminum has a charge of 3 plus. The oxide ion, I use the periodic table, tells me a charge of 2 minus. I'll go through the same sort of thing. Do my pluses balance out my minuses? They don't. I need more minuses. So I'm going to add in another oxygen. Oxide always, always, always comes with a 2 minus. Now I've got too many minuses. I need more positives. I've got another aluminum. Aluminum always comes with a 3 plus. Now I've got 6 pluses and 4 minuses. Still doesn't work. Add in another minus. Now I have a balance between my positive and my negative charges. I have 2 aluminums, Al2, and I have 3 oxygens for Al2O3. And that's how you come up with chemical formulas. You always need to have enough of each to balance out your pluses and your minuses. And so this is just, again, kind of walking us through the same thing. This is sodium coming together with sulfur, like we talked about. The 1 is assumed. But look at what happens here. This is what I mentioned with the crossover rule. Sodium was a 1 plus. That's going to become the subscript. That 1 becomes a subscript now on the sulfur. Sulfide is a 2 minus. That becomes our subscript on the sodium. And then we just omit the 1 because it's understood. So we get Na2S. Let's look back at these that we looked at to see if that holds true. Sure enough, Na and Cl, 1 and 1. For Mg, Cl2, our 2 from magnesium became our subscript 2 for our chlorine. Our 1 for chlorine became our subscript 1 for magnesium, and so forth. It worked here. It worked here. Our 3 from aluminum became our subscript for oxygen. Our 2 for oxygen became a subscript for aluminum, Al2O3. And so this crossover rule will always work. But you also have to remember that we're looking for ionic compounds in particular, we are looking for the lowest whole number ratio. And so let's look at just another example. If we have barium and oxygen, periodic table tells us barium with its 2 plus, oxygen with its 2 minus. Our pluses balance out our minuses. So we only need one of each. We get BaO. If you use the crossover rule here, then you're going to get 2 of each. And you might be tempted to do this. That is okay if you recognize that that's going to be an intermediate step. If you recognize that you can then reduce that down. The same way that in math class, if you were sitting in your 10th grade math class and you came up with an answer of 4/8, your teacher probably would have made you reduce that down to 1/2. Same thing here. You would get Ba2O2 and then just reduce that down to BaO. You will always do that, or you would always have to do that with ionic substances. Ionic substances are always the lowest number whole ratio. It's not the same with covalent compounds and molecular compounds when it's 2 nonmetals. We'll talk about those more later on. But with ionic substances, always, always, always the lowest whole number ratio. And so keep that in mind. It's okay to come up with Ba2O2 if that's part of your process, but just make sure that you're then reducing it down to BaO. So if it's a polyatomic ion, the same rules apply. We still want to balance out our positive and our negative charges. And you can still even use the crossover rule. Na1 plus and NO3, our nitrate ion with its 1 minus, 1 and 1. And so we would just simply write NaNO3. We have to be mindful, though, if we have situations where we need to have more than one polyatomic ion in our formula. And so what I mean by that is, for instance, in order for magnesium and nitrate to come together, magnesium with its 2 plus and nitrate with its 1 minus, we can see from our crossover rule or just analyzing the charges, we can see that we need 2 nitrates. Now, it's important for us to recognize that those 2 nitrates, or that nitrate in general, I mean, nitrate is this thing here. We'll talk more about structures later on, but this is what nitrate really is. It's this thing with nitrogen attached to 3 different oxygens all around it. And so our formula that we write has to somehow show that it's 2 of that entire structure, 2 of that whole thing. And so we put parentheses around our polyatomic ions if we have more than one. And so it's Mg parentheses NO3 with a 2 now as our subscript on the outside. That tells us that we have 2 of the entire NO3 ion. That is key when you're writing chemical formulas. If you do not have those parentheses in cases like this with more than one polyatomic ion, it is wrong. And the rules for formulas and names are very, very strict. Missing those parentheses will be 100% wrong every single time. And so that's something that we do have to keep in mind. And so let's look at a few practice questions. And so we want to come up with the formula for the various ionic compounds that we show. So sodium and bromine. So as we go through these, I'm just going to sort of scroll through them, but feel free to pause the video at each one and come up with the formulas, and then we'll look at the answer. So sodium and bromine, NaBr. Sodium and oxygen, Na2O. Aluminum and chlorine, AlCl3. Barium and chlorine, BaCl2. Aluminum and oxygen, Al2O3. Magnesium and oxygen, MgO. And now a few more, but now we're going to have some polyatomic ions thrown in. So aluminum and sulfate, Al2SO4 3. Magnesium and hydroxide, MgOH2. Potassium and acetate, KCH3CO2. Just a note on acetate really quick. You might see acetate written in two different ways, and it's the same thing, it's still acetate. You might see it written as I just had it written there as CH3CO2. Sometimes you also see it written as CH3COO. Sorry, too many H's there. Just like that. CH3COO. So in either case, it's still the 1- acetate ion. But just be aware that you might see it written with the O's written out like that, or possibly not. Just it'll just depend on how somebody chose to write it, but it's still the same thing. And so lastly, calcium and nitrate, CaNO3 And so that takes us through then how to write a chemical formula. What we're going to shift to now is how we actually name compounds. The naming of compounds, again, also follows very strict rules that we have to follow. When we name a compound, just like when we write the formula for a compound, we always have the cation first and then the anion second. And if it's in the cases of simple cases like this, if we have simply two monatomic ions coming together, then all we do is we use the name of the ions. And so sodium, remember the sodium 1+ ion, cations are just the name of that element, so just sodium. Negatively charged anions, now we modify the name. Instead of bromine, it's bromide. And so NaBr, the actual name of that compound, is sodium bromide. MgCl2, magnesium chloride. AlN, aluminum nitride. You'll note that the 2 here does not come out into the name at all. We don't need it. The reason we don't need it is because what we can do is we can come up with that 2 from the name. We can come up with our chemical formula directly from the name of the compound. And so if I tell you the name sodium chloride, then you're going to go through the process that we just went through in order to be able to come up with the formula. And so sodium, whoa, what's happening there? Okay, sorry. I don't know what just went on. Technology. And so if we're going back and forth, I give you the name sodium chloride. So your process would be, okay, sodium, that's Na. I use the periodic table. Tells me sodium is a 1+. Chloride is Cl. Periodic table tells me the charge on that is going to be 1-. And so I can come up with the formula NaCl. Sodium oxide, which was our other example on that slide. Sodium with its 1+. Periodic table tells me, however, there's oxygen, that oxide will have a charge of 2-. And so I know that my formula has to be Na2O. And so we're able to simply come up with the formula from the name. And so this 2 does not have to show up anywhere in my name because I can find this simply from the name of the compounds because I know what the charges have to be. And so I would come up with these formulas from those names. Now that is if you have metals that are either in the first or second column here, or you're working with maybe, sorry, right behind me, something like aluminum that is definitely going to be a 3+. You know, sodium's always going to be a 1+ no matter what. Calcium is always going to be a 2+ no matter what. When we get to transition metals, now things are a little bit different. And so transition metal, something like iron, could either be a 2+ or a 3+ charge. And so that means that we can't necessarily find the formula from the name without adding some additional information in there. And so in other words, if I just tell you iron oxide, you've got no idea if I'm talking about iron 2+, which would give us a formula of FeO, or am I talking about iron 3+, which would give us a formula of Fe2O3. Two very, very different compounds from each other. The first one, FeO, I can't think of much of what that one would be used for, but Fe2O3, there's rust. That's what rust is. And so these are very different compounds from each other. And so the name iron oxide, without any additional information, doesn't tell me which one of these that I'm talking about. And so our name, when we're working with transition ions, has to have some additional information in there. So we use a Roman numeral to indicate that charge, just like we talked about earlier. And so if I'm talking about iron with a 2+ charge, that's going to be iron 2. Iron with a 3+ charge is iron 3. And what you have to do when you're coming up with the name is use some of the, or sorry, I'll come back to that. So your name indicates which iron that we're talking about. And so in this case, iron with a 2+ charge forming FeO becomes iron 2 oxide. Iron with a 3+ charge for Fe2O3, the name of this compound must be iron 3 oxide. So when you have the formula, though, if you just have FeO and Fe2O3, if you have the formula and you're trying to come up with the name, you have to use other information in the compound to figure out what the charge is going to be. And so, in other words, with these examples right here, and so I have FeO. If I have FeO and I have Fe2O3, I know that oxygen is always going to be a 2-, no matter what. I just know that that's what oxygen is. It's not one of the transition metals. It's not going to have differing charges. Oxygen will be a 2- charge. In the case of FeO, so if oxygen is a 2- charge, oxygen is a 2- charge, I only have one of each in this particular formula. Right? I've got one oxygen and one iron. That tells me that this iron has to be a 2+. And so I would come up with the name iron 2 oxide, as opposed to my second one. Now, oxygen is always going to be a 2-, and I have 3 of them now. I have 2 irons according to my formula. So in order for these to balance out, each of these irons must be a 3+, leading me to the name iron 3 oxide. And that's all there is to it. In the case of these two examples here, so same exact idea, but now we're working with some chromium metal as our transition metal. So Cr2O3, you would go through the same process, and you would say that, okay, 3 oxygens minus 2 for a total of -6. 2 chromiums, in order to get to +6, they each have to be 3. Chromium 3 oxide. Cr2O7, total of 14-. So each of these chromiums must be a +7. Chromium 7 oxide. You can also, if you want a shortcut, and I know many of you do, use your crossover rule in reverse. 3. Chromium 3. 7. Chromium 7. And so when you have a transition metal, so any of these transition metals here in the center of our periodic table, you always have to indicate the charge of the metal by using Roman numerals. Now, unfortunately for you, and many times when a chemistry teacher says always, they're about to give you some exceptions. And that's the case here. It turns out that silver, cadmium, and zinc are actually exceptions to this. So right here in the upper right of our transition metals, silver, cadmium, and zinc, they actually, for reasons that we're not going to really get into at this point, their charges are fixed. Their charges aren't going to change. Silver is always going to be a +1. Cadmium and zinc will always be a +2. And so in those cases, the name absolutely gives you enough information. Silver iodide, I know that silver is a 1+, iodide is a 1-, so silver iodide must be AgI. I have no idea why I threw an extra H onto there. Maybe zinc chloride. I know that zinc is always going to be a +2, chloride is a -1. So I get ZnCl2. So those are exceptions, silver, cadmium, and zinc. Now let's talk about naming compounds that involve polyatomic ions. These are maybe the simplest you're going to encounter. The name of the polyatomic ion is the name of the polyatomic ion. Use it. NaNO3, NO3 is nitrate. So that becomes sodium nitrate. FeNO3, okay, now we have to use what we talked about before. We know the charge of nitrate is a -1. We have 3 of those. So that means that this must be iron 3 nitrate. Iron's a transition metal, so we have to indicate the charge on the iron atom, iron ion. Na3PO4. PO4 is phosphate, so we have sodium phosphate. NH4Cl. NH4 is a 1+ ammonium ion. We get ammonium chloride. And so the polyatomics are simple in that respect, that you just simply use the name of the polyatomic ion. Now this, hopefully you're starting to see as well already, why it is so important to know and recognize the names of the polyatomic ions. If you did not know that nitrate was NO3 and you saw this, you would be tempted to name this something like sodium nitrogen oxide. And that's not it. That's not what it is. It is sodium nitrate. You would be tempted to maybe name this, sodium phosphide oxide. But that's not what it is. PO4 is phosphate, and we have to recognize that as such in the name. So we have to be able to recognize these polyatomic ions. So again, here's some practice. Instead of going through these one by one, I'm just going to ask you to pause the video now, try to name these various compounds. Sorry, I see a mistake in here that I'm going to correct right now while I'm thinking of it. That had an extra H in there. That's better. Okay, so go ahead now and pause the video now and come up with the names for these chemical compounds. Insert Jeopardy theme if you'd like. Do, 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 do. On another note, and some of you probably aren't, I hate to say this, but aren't quite old enough to appreciate it, but Alex Trebek, there's a tremendous loss. Alex Trebek has been a phenomenal Jeopardy host for years. Anyway, hopefully you came up with the various names here. Oh, let me fix that one right in here too. There we go. Okay. And so NaCl, sodium chloride, MgCl2, magnesium chloride, FeCl2, iron 2 chloride, NaCH3COO, sodium acetate, FePO4, iron 3 phosphate, and finally ammonium nitrate, that NH4NO3. And so those are all the rules for how we go about naming ionic compounds. We have a totally different set of rules now for naming molecular compounds, but for naming compounds when non-metals come together. The reason for this is that non-metals don't come together in the same predictable ways that a metal and a non-metal do. When sodium and chlorine come together, sodium forms a 1+ ion, chlorine forms a -1 chloride ion. They are always, always, always going to come together as NaCl. There's no other way that sodium and chlorine are going to come together. There's no other way that aluminum and oxygen are going to come together other than Al2O3. And so aluminum and oxygen, Al2O3. So the name aluminum oxide will always, always, always lead you to this formula every single time. That's the only way they're going to come together because of the charges on the ions. When we're talking about molecular or covalent compounds, we're not forming ions now. And that should make sense to you, because when we're talking about covalent compounds, remember, we're talking about two non-metals coming together. Non-metals, when they form ions, form negatively charged ions. So you're not going to have a negative and a negative coming together to form something. And so with two non-metals, we're not talking about ions forming. They share their electrons. We'll get into that dynamic later on in the course. But they don't lose or gain electrons in order to come together to form a compound. What that does is that can lead to a number of different ways that they can come together. And so nitrogen and oxygen, for instance. Nitrogen and oxygen can come together like this. They could 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 even come together like this or like this. And these are all ways that they really do exist in nature. We also, now when we're talking about nonmetals and covalent compounds, we don't reduce them down in the same way that we did ionic compounds. N2O2 is really the way that that particular compound would exist. N2O4 is the way that that particular compound would exist. And so now what we need is a naming convention. We need a set of naming rules that tells us what combination we're talking about. It is no longer sufficient for me to simply write nitrogen oxide, because you have no idea with that information which of these that I'm referring to. And so now what we're going to do for molecular compounds, for covalent compounds only, we are going to use this set of prefixes to specify how many of each atom we have. And so most of these you're familiar with, mono, di, tri, certainly, maybe tetra for 4, you might not be that familiar with, but penta for 5, hexa, hepta, octa, nona, and deca may be a little unfamiliar to you, but many of these are familiar prefixes to you. We now use these, again, to identify how many of each element we have. So some examples here. BCl3, boron, trichloride. SO3, sulfur trioxide. NO, nitrogen monoxide. Note that we do have the extra O in there. Sorry, we don't say monooxide. It is just monoxide. We also don't write mono if it's the first element. And so there are no monos in front of any of these. That's only if it's the first element, though. If it's the second, we absolutely do write it. So nitrogen monoxide. N2O4, dinitrogen tetraoxide, and so forth. If we look at the examples that I just gave with all of the different nitrogens and oxygens, let's just go through what these would be. And some of these we've already seen. So we have nitrogen monoxide. We have dinitrogen monoxide. Dinitrogen. Oh, what do I have going on there? Sorry about that. Clumsy thumbs. Dinitrogen dioxide, and so forth. Nitrogen dioxide, dinitrogen pentoxide, and dinitrogen tetroxide. Sorry, very messy handwriting. I should have taken a little time, been neater there, but you get the idea. And so now go ahead and come up with, go the other way though, come up with the formula from the names of these. So boron trichloride becomes BCl3. Sulfur dioxide. Sorry, sulfur dioxide, SO2. Silicone hexabromide, SiBr6. Diphosphorus pentoxide, PTO5. And so it is very, very, very important to note that you only ever use these prefixes for covalent or molecular compounds when it is two non-metals. Do not use these prefixes, sorry, for ionic compounds. It will absolutely be incorrect. And so if you have, like we looked at earlier, MgCl2, if you write magnesium dichloride, that is absolutely wrong every single time. Remember, the rules for naming compounds are very specific. And so if you add something in that you don't need, or if you're missing something you do need, the name is wrong. This would simply be magnesium chloride. And so go ahead, actually, let's see if I can come up with these examples that I'm thinking of right on the fly here. Go ahead and come up with the names of these various compounds. MgCl2, FeCl2, and what do I want to do next? Yeah, okay, that'll work. And SCl2. So we talked about the rules for all of these different types of compounds. So go ahead and pause the video now and see what you can come up with for the names of these. Okay. Hopefully what you came up with was simply magnesium chloride for the top one. In the bottom, in the second one rather, now we have a transition metal, so we have to indicate that this is in fact iron 2 chloride. And in our last one, now we have two non-metals coming together, so we have to indicate how many of each. So we have sulfur dichloride. Any different combinations for any of these? Magnesium dichloride would be wrong. Magnesium 2 chloride would be wrong because you don't need the charge in there. Iron 3 dichloride, wrong. Iron chloride without that charge, wrong. Sulfur chloride without any sort of dye in there, wrong. It's got to be sulfur dichloride, and so forth. Very, very, very specific naming rules. The last thing we're going to talk about how to name today are naming acids. We're going to talk a fair bit more about properties of acids later and what acids are. For now, we're just going to look at the very basics and how we go about naming them. For the most part, the acids that we are going to be talking about consist of negatively charged anions with the appropriate number of hydrogens thrown in front of it. And so, for instance, if we have I'm not sure what is going on here. Stuff. Okay, that's what's going on. So for instance, if we have a Cl1 minus, it's only got a 1 minus hydrogen with its 1 plus. We would need 1 hydrogen. That the acid made from that would be HCl. Same thing, a fluorine 1 minus would make an acid with hydrogen as HF. NO3, our nitrate 1 minus ion, would form an acid with HNO3. Carbonate, our CO3 with a 2 minus ion, can form an acid now with 2 hydrogens as H2CO3. Phosphate with its 3 minus would need 3 hydrogens, H3PO4. And so these are all various acids here. And so our big clue for acids for now is going to be if you have a hydrogen in front, it's probably an acid. So we have to look at how to name these. If we're looking at sort of the generic acid, a hydrogen in front with something for a negatively charged ion, we're just going to call that HX, where the X could be anything for an ion. Now, if that X is a halogen, if that X is one of these elements here, then all we do for the name is hydro in the front of it, and then the base name of the halogen, and then followed by ic acid. And so, for instance, if it's Cl, if it's HCl, hydrochloric acid. HBr, hydrobromic acid. HF, hydrofluoric acid. HI, hydroiodic acid, and so forth. If the X is one of our polyatomic ions, then it gets a little bit more difficult, but still not bad. If it's a polyatomic ion that ends with 8, then again, we sort of cut off the end of it and then replace it with ic acid. And so NO3, so remember NO3 was our nitrate ion. So we cut off the end of nitrate and instead call it nitric acid. Phosphate, our PO4 ion. We cut off the 8 at the end and instead put oic acid. And so instead of phosphorus, it's phosphoric acid. If it's a polyatomic ion that ends in ite, then we change it to us acid. And so NO2 was our nitrite ion. And so HNO2 becomes nitrous acid, and so forth. And so that's how we name acids. And so the last thing that I just want to show you today, because I know there's a lot of various information, especially when we get to the naming rules, because it's so very specific, the type of rule that we use for the type of compound we have. And so what I've put together is a flow chart that you can use. And so right here, just as a reminder for how the web page is set up as well, if you go to the CHY 113 web page, we go to Unit 1 Materials. There's a whole slew of various resources here for you. For one thing, all of the lecture slides that I use. And so today we finished off the slides associated with this lecture here. But also, you'll see some various informational handouts. And one of those for this unit is a compound naming flow chart that I've put together. This will help you keep some of the rules straight. If you're a flow chart sort of person, then this will help you out. And so the first thing that you have to do, if you're presented with a question that wants you to name a chemical compound, first thing to do is ask yourself, okay, is this an ionic or a covalent compound? To answer that, say, well, is there a metal there? Is there any metal present? Or the NH4 ammonium ion? If any of those are present, then yes, this is ionic. So we're going to name with our positive ion first. Then we ask ourselves, is our positive ion ammonium? Is it a main group metal, meaning rows 1 and 2, or aluminum pretty much? Or is it a transition metal? From there, we would follow the appropriate pathway If it's a main group metal, we just use the name of the atom. If it's a transition metal, we just use the name of the Roman numeral. If it is ammonium, then that's just the name of it. And from there, we go to naming our negative ion. Is it monatomic or is it polyatomic? And then we see some examples at the end of that pathway here. If it turns out that there's no metal or ammonium, if it's both nonmetals, then we're dealing with a covalent or a molecular compound. Is it an acid? Does it start with an H? Then we're going to flow through our acid naming rules that we just talked about. If there's no H there, it's not an acid. And so we're going to use our prefixes. So feel free to use this flow chart if it does help you as you learn how to apply the various rules to all the different names that or all the different naming conventions that we talked about. And so that is it for today. And so that sort of wraps up our discussions of compounds and atomic structure that we talked about last time. Looking ahead a little bit, we're going to start talking a little bit next time about how we count various atoms and some of the conventions that we use there. And then we'll start talking a little bit about chemical reactions. But believe it or not, this brings us now to about halfway through Unit 1. So we're already starting to look ahead and think towards our first test a little bit, which will be coming up before you know it. And so, as always, if you have any questions, definitely feel free to shoot me an email. In the meantime, everybody have a great day.